The story begins not with a bang, but with a hush. Imagine standing on the shore of an ocean so vast that its horizon is not a line, but a blur, an infinite curve where sky and sea dissolve into one another. The cosmos is that ocean, swelling, receding, reshaping itself in slow, imperceptible tides. Yet unlike any earthly sea, it bears no sound, only a silence as deep as time itself. And somewhere in this silence, hidden behind the veil of billions of years, lies a question that refuses to rest. What happens when the universe itself reaches its end? This question is not simply one of physics, but of existence itself. To ask about the end of the universe is to ask about the fate of stars, of matter, of memory, of us. It is to peer beyond the lifetime of everything we know, into a realm where time itself may surrender its grip, where the very fabric of space could unravel, or freeze, or ignite anew. The universe, once thought eternal, bears within it the seeds of its own mortality. The night sky we see today is a patchwork of histories, the faint light of galaxies traveling across eons, the afterglow of the Big Bang etched into microwaves, the restless whisper of expansion still accelerating in the dark. Every photon carries a message from a past that was once a present. But if we lean far enough into imagination, those same photons ask us to look forward toward a distant horizon, when stars will no longer burn, when galaxies will drift into the unreachable, when even atoms may dissolve into nothingness. And yet, the end is not singular. It is a spectrum of possible fates, each rooted in mathematics, in data, in bold speculation. Will the cosmos expand until it freezes into stillness? Will it tear itself apart in an unimaginable rip? Will it collapse inward, returning everything to a singular beginning? Or will it shatter into something stranger, a quantum flicker, a vacuum collapse, a rebirth in another form? The end of the universe is not merely a scientific curiosity. It is the final poem written into the structure of space-time, a message that speaks of impermanence, of transformation, of the delicate balance between being and nothing. To explore it is to drift into the deepest currents of cosmology and philosophy alike, for in contemplating the death of the universe, we contemplate the meaning of life within it. And so the journey begins, at the shoreline of eternity, where the waves are galaxies, the tide is expansion, and the question of the end waits like a shadow beyond the horizon. The great mystery of endings began, paradoxically, with a discovery of beginnings. In the early decades of the 20th century, astronomers turned their telescopes toward the faint smudges of light that lay beyond the familiar Milky Way. At first, these nebulae were debated curiosities. Were they clouds of gas inside our own galaxy, or vast systems of stars far beyond it? The work of Edwin Hubble, building on the insights of Henrietta Swan Leavitt, would resolve the question, and in doing so, open a new wound in humanity's understanding of the universe. Leavitt, meticulously studying variable stars called Cepheids in the Magellanic Clouds, uncovered a relationship between their brightness and their pulsation periods. What she found, quiet and precise, was a tool to measure the universe itself. This period luminosity relation transformed Cepheids into standard candles, beacons whose intrinsic brightness could be known and whose distance could be measured. With her discovery, light became a ruler stretched across the cosmos. Hubble took that ruler and pointed the 100-inch Hooker telescope at Mount Wilson towards spiral nebulae. What he found in 1924 was decisive. The Cepheids within these systems placed them far outside the bounds of the Milky Way. These were not clouds, but galaxies, island universes, as Immanuel Kant had once imagined, each a cathedral of stars adrift in infinite dark. The cosmos was suddenly far larger than anyone had dared to believe. But Hubble's revelation did not end there. By examining the spectra of these galaxies, he noticed something stranger still. Their light was stretched, shifted toward the red end of the spectrum. Vesto Melvin Slipher had observed redshifts years earlier, but it was Hubble who gathered them into a pattern. Plotting velocity against distance, he revealed that galaxies were not merely scattered, they were fleeing. Space itself was expanding, and every galaxy was carried upon its current like driftwood on an endless sea. This was the first whisper of a story that would one day end in silence. Expansion meant that the universe was dynamic, not eternal and unchanging. It had a beginning, and therefore it might have an end. The night sky, once imagined as an infinite, steady canvas, was now a restless scene, stretching and thinning, carrying with it implications that reached far beyond imagination. At the time, the discovery was met with awe and disquiet. Albert Einstein himself had introduced a cosmological constant to keep the universe static in his equations of general relativity. To hear that space itself was alive with expansion forced him to admit that his adjustment had been unnecessary, what he called his greatest blunder. And yet, that very constant, abandoned then, would later return as the name for the strange, invisible force accelerating the cosmos into the future. The discovery phase of cosmology was not only about mathematics or telescopes, it was about the shattering of human intuition. For millennia, the stars had seemed eternal. Now, scientists knew they were not. Galaxies were running away from us, the night sky was shifting with time, and the stage on which all stories were told was itself in motion. It was in these moments, in the painstaking work of measuring faint Cepheids, in the careful plotting of spectral lines, that the seed of the ultimate question was sown. If the universe expands, what awaits it at the end of that journey? The sky would never again be seen as still. It was alive, and what lives must also, someday, die. The first murmurs of expansion might have been unsettling, but what followed decades later would become a shock, a revelation so profound that it shook the very foundations of cosmology. It was not enough that the universe was expanding. The deeper question was whether this expansion was slowing under the weight of its own gravity, destined to halt and reverse, or whether it would continue forever, stretching the cosmos thinner and thinner. For much of the 20th century, scientists debated this balance, measuring the density of matter and the geometry of space, weighing the cosmos like a giant scale. The expectation seemed natural. Gravity, the great binder, should resist expansion. Galaxies, though flung outward, should feel the tug of every other galaxy, the combined pull of stars, dust, gas, and invisible dark matter. The universe was a tug-of-war between motion and weight. Would expansion eventually stall and collapse into a fiery big crunch? Or would it coast outward forever, slowing but never stopping, gradually dimming into heat death? But in the late 1990 seconds, an unexpected truth emerged. Teams of astronomers, scanning the heavens for distant Type Ia supernovae stellar explosions bright enough to serve as new standard candles, sought to measure cosmic deceleration. Instead, their data revealed the opposite. The explosions appeared dimmer than expected, farther away than predicted. Expansion was not slowing, it was accelerating. This was a revelation that tore through science like a thunderclap. The universe, instead of easing into stillness, was being driven faster and faster apart by some hidden force. Space itself was not simply stretching, it was stretching with increasing haste, as though compelled by an invisible hand. The galaxies were not merely running away, they were being pushed. For cosmologists, this result was more than surprising. It was terrifying. The equations of general relativity could allow for such a term, Einstein's discarded cosmological constant, but what could this energy be? It was not matter, not radiation, not any familiar form of energy. It did not clump, it did not shine, it did not slow. Instead, It pervaded every inch of space with relentless uniformity, acting as a repulsive gravity, a pressure that drove creation outward. The strangeness of it struck deep. Physics had been built upon the idea that matter attracts, that gravity is the glue of existence. Now there was evidence of a force that did the opposite, a force that caused space to speed away from itself. The cosmos was not simply vast, it was unstable, racing toward a future no one had predicted. The scientific world reeled. The Nobel Prize in Physics would eventually be awarded to the discoverers of cosmic acceleration, but the real prize, the understanding of what was happening, remained elusive. This was not a minor adjustment, not a small correction. It was the discovery that most of the universe, perhaps 70% or more, was composed of something entirely unknown, something that defied intuition and observation alike. Here was the scientific shock. The universe was not only expanding, but accelerating, powered by a form of energy no one understood. What was once thought to be a cosmos bound by gravity and matter was now revealed to be dominated by emptiness itself, or rather, by the energy hidden within that emptiness. This revelation opened a new wound in cosmology, one that remains unhealed to this day, for it meant that the ultimate fate of the universe was far stranger than the steady decline once imagined. The end might not be a simple cooling or a collapse, but something wilder, more violent, or more eternal. The rules were broken, and no one knew how the story would end. When a name is given, it becomes real, and so the invisible hand behind the universe's accelerated expansion was christened dark energy. A phrase at once explanatory and evasive, it told us nothing and everything that something unseen was at work, and that it was powerful enough to dominate all else. The birth of this term marked the moment when physics was forced to acknowledge a vast, uncharted continent within the very vacuum of existence. The idea itself was not wholly new. Einstein had once placed a cosmological constant, will, into his equations to hold the universe still. After Hubble's discovery of expansion, he abandoned it, dismissing it as a misstep. Yet in the light of supernovae surveys, will returned with unsettling elegance. It could be reinterpreted as vacuum energy, a pressure intrinsic to space itself, capable of driving acceleration with a simple, ruthless persistence. Still, a name is not an answer. Dark energy may be uniform, invisible, and everywhere, but what is it? Theories proliferated like shadows. Perhaps it was a true constant, an immutable property of space-time, or perhaps it was a dynamic field, evolving with time, its strength waxing or waning in ways yet unseen. Physicists spoke of quintessence, phantom energy, and scalar fields, each a mathematical attempt to clothe the mystery in equations. What startled scientists most was the scale of the revelation. Ordinary matter, the stars, planets, dust, and galaxies we see amounted to less than 5% of the cosmos. Dark matter, unseen but inferred by gravity's pull, made up around a quarter. But dark energy, this enigmatic accelerant, commanded nearly 70%. The universe, once thought to be a grand collection of matter, was in fact ruled by a featureless void, an emptiness more influential than all the galaxies combined. The implications were staggering. A cosmological constant that emerges naturally from quantum field theory should be vast, unimaginably large, perhaps 120 orders of magnitude greater than what we observe. Why then is it so small? Why does it exist at all? This mismatch between prediction and measurement is often called the worst theoretical error in physics. It forces scientists to wonder if something deeper is hidden beneath, a structure or principle that has yet to be unveiled. Dark energy thus became both a placeholder and a haunting. A placeholder because it allowed equations to fit data, a way to write acceleration into the language of relativity. A haunting because it revealed our ignorance, a reminder that most of the cosmos is a stranger we cannot touch, taste, or measure directly. It is this haunting that makes the end of the universe so unknowable. If dark energy is constant, then the cosmos will race outward forever, thinning into cold silence. If it grows stronger, galaxies, stars, and even atoms may be ripped apart in a catastrophic finale. If it decays, perhaps expansion will slow, halt, or even reverse into collapse. The destiny of everything depends on the nature of this shadow force. In naming it, humanity admitted both triumph and humility. Triumph, because we had glimpsed a hidden truth written into starlight. Humility, because we realized how little we truly know of the sea upon which our world drifts. Dark energy is not merely a scientific concept, it is the reminder that the universe's script is still being written, and that its ending remains a secret kept by the very fabric of space. Gravity has always been the universe's most familiar companion. It is the sculptor of orbits, the binder of galaxies, the unseen hand that steadies the fragile dance of stars. To think of gravity is to think of attraction, of pull, of the inexorable tendency of matter to gather, to coalesce, to fall together. Yet with the discovery of cosmic acceleration, this deepest of intuitions was fractured. The equations of relativity, once a map of how mass bends space-time into the geometry we call gravity, revealed themselves capable of harboring something stranger, a term that made space push rather than pull. Einstein's general relativity is not a law written in stone, but a tapestry woven from geometry. Mass tells space how to curve, space tells mass how to move. For nearly a century, this dance seemed harmonious, a symphony of attraction. But when cosmologists reintroduced the cosmological constant to explain acceleration, the harmony shifted into something uncanny. Instead of all things falling together, space-time itself was driving them apart. This reversal was not merely odd, it was paradigm-breaking. The very idea that emptiness could act as a source of energy challenged our understanding of physics at its root. Vacuum, once imagined as absence, now revealed itself as presence, a seething sea of potential, exerting pressure on the cosmos itself. And yet this pressure did not slow time or gather matter. It did the opposite. It forced the universe to expand with ever-increasing urgency. The shock was philosophical as much as scientific. If gravity could repel as well as attract, then the ultimate trajectory of the cosmos was no longer governed solely by mass and motion. Instead, it was governed by a mystery built into the vacuum itself. The equations of relativity, which had always been considered complete in their elegance, suddenly felt incomplete. The fabric of the universe was not only curved, but restless. What does it mean for physics when one of its oldest rules bends in this way? Newton's apple fell downward because of attraction. Galaxies cluster because of gravity's pull. But when space accelerates apart, we are forced to confront a symmetry broken at the heart of intuition. A universe driven outward suggests not stability, but instability, not permanence, but impermanence. This realization unsettled cosmologists. If the rules of the game could flip so profoundly, what else might be waiting, hidden beneath the mathematics? Dark energy's repulsion was not just a correction, it was a reminder that our most cherished frameworks might be provisional, fragile, and incomplete. And it was here that the story of the end of the universe took a more haunting turn. Because if gravity itself could be inverted by the emptiness of space, then the universe's fate could no longer be trusted to familiar expectations. Heat, death, collapse, or rip. Each possibility flowed not from the comforting laws of attraction, but from the alien force of repulsion hidden in the vacuum. The canon of physics, once confident in the unity of its rules, now contained a fissure, a silent fracture opened by acceleration, a reminder that even the strongest laws may bend in ways we have yet to imagine. And in that bending, the destiny of everything hangs suspended. The shock of a repulsive cosmos demanded proof stronger than the flickering of distant supernovae. It required instruments capable of measuring not just the brightness of a dying star, but the very pulse of the universe across its entire history. And so, one by one, humanity launched new eyes into the dark machines of extraordinary precision designed to transform the sky into a ledger of expansion. The first great leap came with the Cosmic Background Explorer, COBE, in 1989. Its task was to listen to the faintest echo of creation, the cosmic microwave background, the afterglow of the Big Bang itself. COBE revealed a near-perfect blackbody spectrum, confirming that the universe had indeed erupted from a hot, dense beginning. More than that, it measured minute anisotropies, tiny ripples in temperature that mapped the seeds of galaxies. For the first time, cosmology had a portrait of the universe's infancy, a baseline against which its later life could be measured. Next came the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001, sharpening COBE's map with astonishing clarity. WMAP transformed vague hints into sharp contours, allowing cosmologists to measure the age of the universe, the density of its matter, and the strange dominance of dark energy with far greater certainty. Suddenly, expansion was not an abstract curve, it was a number, a history written into radiation itself. Then, in 2009, the Planck satellite raised the resolution still further, mapping the cosmic microwave background with precision so fine it approached the limits of what physics could offer. Planck's results refined the proportions of the cosmic recipe, about 4.9% normal matter, 26.8% dark matter, and 68.3% dark energy. The numbers, cold and exact, confirmed that most of reality is made of the invisible and the unknown. But telescopes on Earth also joined this chorus. The Sloan Digital Sky Survey, SDSS, mapped galaxies across billions of light years, detecting subtle imprints of sound waves frozen into their distribution, the so-called baryon acoustic oscillations, BAO. These cosmic ripples acted as standard rulers, stretching across the cosmos, revealing how expansion has accelerated over time. Together with weak lensing surveys, which trace how gravity distorts light across the cosmic web, they confirmed what supernovae had first suggested. Acceleration is real, and it is relentless. Each of these instruments lengthened our horizon, allowing us to see not just the distant past, but the trajectory of the future. The universe's story was no longer speculative. It was written in spectra, in ripples, in frozen echoes of sound and light. And the story, as these instruments told it, left no room for a static cosmos. What emerged was a tightening of possibilities. A constant dark energy fitted the data well, the cosmological constant reborn. Yet, alternative models remained alive, whispering of quintessence or evolving fields. Each new mission, each sharper map, narrowed the corridor of fates. Heat-death rose in likelihood, while collapse receded into the background. The Big Rip lingered as a possibility, depending on whether the pressure of dark energy proved stronger than expected. Science had moved beyond wonder alone. It now wielded tools that transformed the universe into data and data into prophecy. And though prophecy is never perfect, the outlines of the end were becoming clearer. With every pixel of the microwave sky, with every ripple in the clustering of galaxies, the noose around our possible endings grew tighter. The cosmos had become an experiment on a scale beyond imagination. Telescopes and satellites, placed like sentinels at the edges of human ingenuity, had turned the heavens into a laboratory, a place where the fate of all things could be measured, catalogued, and perhaps, someday, understood. If telescopes revealed the great expansion, thermodynamics whispered its consequence. Long before dark energy's repulsive hand was known, physics had already uncovered a quiet, inescapable current beneath the universe, the climb of entropy, the slow and patient drift of order into disorder. The laws of heat, first written to explain steam engines and furnaces, proved to be cosmic laws, binding not only machines but stars, galaxies, and time itself. Entropy is the measure of disorder, the count of possible arrangements that a system can take. In a young universe, freshly born from the fireball of the Big Bang, energy was dense, concentrated, and dynamic. Out of this came galaxies, stars, planets, and eventually life. But with every transformation, energy spread, evened out, dissipated. Stars burn hydrogen into helium, releasing light into the void. Black holes devour matter, but also radiate faintly into darkness. Every event increases entropy, nudging the universe one step closer to a state of balance, a state where no change is possible, because everything is the same. This is the long, patient climb toward heat death. It is not fire and collapse, but silence and equilibrium. Imagine a universe where no gradients remain, no hot against cold, no dense against empty, no flame against shadow. Without differences, no work can be done, no processes can unfold. Time itself, which gains its direction from the arrow of increasing entropy, would lose its meaning. In such a cosmos, not only would stars be gone, but the very concept of before and after would dissolve into irrelevance. The scale of this destiny is staggering. Stars will burn for trillions of years before they exhaust their fuel. White dwarfs will cool into black dwarfs. Protons, if they decay, will vanish into radiation. Black holes, given quadrillions upon quadrillions of years, will evaporate through Hawking radiation, leaving nothing but a thin bath of photons and neutrinos. Every step is slow, drawn out beyond human comprehension, yet relentless. The direction is set by the second law of thermodynamics, as steady and inevitable as a falling tide. And so, even before dark energy was named, entropy had already written one possible ending for the universe. Expansion might carry galaxies apart, but entropy ensured that whatever shape the cosmos took, it would end in uniformity. Heat death was the slowest of apocalypses, the unwinding of structure, not in violence, but in exhaustion. There is something hauntingly poetic in this vision. No cataclysm, no sudden collapse, only the stretching of time until all lights fade. The universe would end not with fire, but with forgetting. Every memory encoded in matter, every pattern written in atoms, would be dissolved into randomness until only silence remains. For scientists, this fate is at once terrifying and oddly comforting. Terrifying because it suggests an absolute end to meaning and change, comforting because it is gentle, inevitable, and free of violence. Heat death is not an explosion but a lullaby, the last breath of a cosmos that once blazed with stars. It is here that entropy reveals its double role, both the enemy of permanence and the narrator of time. Without it, processes would not unfold, stars would not burn, life would not emerge. With it, all of these things must one day cease. Entropy is the universe's clock, and it ticks in only one direction. The more carefully cosmologists traced the lines of expansion and entropy, the clearer it became that the universe was not marching toward a single, inevitable destiny. Instead, it stood before a branching corridor of endings, each dependent on the properties of dark energy and the geometry of space. To map the universe's fate was to create a taxonomy of doomsday scenarios, a list of possibilities that balanced on the edge of known physics and speculative imagination. The most familiar was the heat death, the quiet equilibrium dictated by the second law of thermodynamics. If dark energy is a true constant, expansion will continue forever, Galaxies will vanish beyond each other's horizons, stars will fade, black holes will evaporate, and the universe will drift into a thin, cold mist of radiation. This is the slow unweaving of all structure, not destruction, but erasure. Another branch was the Big Rip, a fate that depended on dark energy's equation of state. If its pressure is stronger than that of a cosmological constant, galaxies would not merely drift apart but be torn apart. The Milky Way would fragment, solar systems would unravel, planets would lose their orbits, and eventually even atoms themselves would be shredded. The end would not be slow, but catastrophic, occurring on a timescale far shorter than heat death. A third option was the Big Crunch, once considered a real contender before observations tilted against it. If dark energy were to reverse or vanish, gravity could regain dominance, pulling galaxies inward. The universe would collapse back into a dense fireball, echoing the Big Bang in reverse. Though data suggests otherwise, the possibility lingers as a reminder of how delicately fate depends on unseen parameters. And then there were cyclical models, where the universe does not end at all but oscillates, expanding, contracting, rebounding in endless rhythm. Some theories, drawing from string cosmology and higher dimensional physics, imagined universes colliding and rebirthing in cycles beyond counting. In these visions, endings are beginnings, and death is metamorphosis. Finally, quantum theory introduced another strange path: vacuum decay. If our universe exists in a metastable state, a deeper energy minimum may lurk beneath. A bubble of true vacuum could appear, expand at light speed, and erase everything: stars, galaxies, even the laws of physics themselves. This fate would arrive without warning, instantaneous and absolute. Each of these scenarios carried with it a different texture of terror and awe. Some were slow and melancholic, others violent and abrupt. Together, they revealed how fragile our understanding truly is. The universe could linger for unthinkable eons, or vanish in an instant. What was once thought of as eternal sky had become a stage of precarious possibilities, and the question of endings was no longer a philosophical musing, but a scientific riddle. Expansion had made the cosmos restless, and dark energy had made it unknowable. To live in such a universe is to live with the knowledge that everything, from the smallest particle to the largest cluster of galaxies, is balanced on the edge of mystery. Among the branching corridors of cosmic endings, none feels more inevitable and more desolate than the slow march of heat death. It is the scenario that emerges naturally if dark energy remains constant, if expansion continues indefinitely, if the arrow of entropy points ever upward without reprieve. Unlike the sudden violence of a Big Rip or the dramatic implosion of a Big Crunch, heat death is a silence that spreads, a dimming of the stars into a universe that forgets itself. The sequence begins with the exhaustion of stellar fuel. Over the next trillions of years, galaxies like our Milky Way will fade as their stars age and die. New stars will form for a time, from the gas left behind by supernovae, but eventually the raw material for creation will be spent. What remains will be a dwindling population of long-lived red dwarfs, glowing faintly in the darkness. Even these, after tens of trillions of years, will cool and darken into black dwarfs, cold remnants of once burning stars. Then, if protons are unstable, decay will eat away at matter itself. Experiments have not yet confirmed such decay, but many grand unification theories predict it. Should this be true, black dwarfs, neutron stars, and even planets would slowly dissolve into radiation over unimaginable stretches of time. If protons endure, the decline will be slower but not less certain. Matter would persist, but inert, lifeless, spread too thinly across an ever-expanding void to gather into anything new. Even black holes, the densest repositories of gravity, cannot resist eternity. Hawking showed that quantum effects allow them to radiate, to evaporate, particle by particle, until even the supermassive black holes at galactic centers vanish. The timeline of their disappearance is staggering, some 10 to the power of 100 years for the largest. Yet no clock is long enough to resist entropy. What remains beyond this epoch is a universe of faint, low-energy particles, photons stretched to enormous wavelengths, neutrinos wandering through the void, and perhaps a whisper of dark matter that itself may one day decay. Temperature trends toward uniformity. Structure dissolves. The cosmos becomes smooth, empty, featureless. In such a universe, time itself loses its direction. The arrow that points from past to future gains its meaning from entropy's climb. When maximum entropy is reached, the difference between then and now evaporates. Change no longer exists, because there is no imbalance to drive it. The future becomes indistinguishable from the present, a static sea of cold silence. There is something hauntingly intimate about this vision. It does not end in fire, but in forgetting. A star does not explode, it simply fades. A galaxy does not collapse, it vanishes beyond horizons. Even memory, encoded in the arrangements of matter, dissolves into randomness. In the stillness of heat death, no witness remains, and no trace of what once was can be recalled. Yet in that quiet lies a strange kind of beauty. Heat death is not destruction, but return to equilibrium, to balance, to a silence that holds no tension. The universe that once blazed with stars, birthed life, and told stories through galaxies would rest at last. It would not scream, it would sigh. And so, the slow unweaving becomes not only a scientific possibility, but also a cosmic poem. The universe, having lived through creation, growth, and brilliance, may choose to end in stillness, a final, infinite pause that is less a death than a surrender to peace. If heat death sketches the slow fading of stars, then black holes trace the farthest frontier of this decline. They are the last great structures, the stubborn knots of gravity that resist entropy's smoothing hand. In the far future universe, when galaxies have dimmed and stellar births have ceased, black holes will remain as the final storytellers, vast, silent, and seemingly eternal. But even they, the most enduring fortresses of space-time, cannot last forever. To understand their role in the universe's end, one must revisit the discovery that black holes are not perfectly black. In 1974, Stephen Hawking revealed a paradoxical truth. Through the quantum flickering of vacuum near the event horizon, black holes emit radiation. Pairs of virtual particles, conjured briefly from nothing, can be split by the horizon, one falling inward, the other escaping outward. To an observer at a distance, the black hole appears to radiate, to lose energy, to evaporate. The process is agonizingly slow. A black hole the mass of a star takes on the order of 10 to the power of 67 years to vanish. Supermassive black holes, millions or billions of times the mass of the Sun, stretch this timescale to 10 to the power of 100 years or more. These numbers defy imagination. They are not simply large, they make the current age of the universe, a mere 13.8 billion years, look like an instant, and yet, in the arithmetic of eternity, evaporation is certain. As eons pass, black holes will dominate the landscape of a cooling cosmos. Galaxies will dissolve, stars will vanish, but black holes will sit in the void, slowly consuming stray matter, merging when they meet, and shrinking imperceptibly as they radiate. The universe will become a kingdom of horizons, each one marking a silent monument to the energy trapped within. Then, one by one, they will begin to die. As their mass diminishes, the temperature of Hawking radiation rises. Black holes, once cold and dark, will flare briefly with a final burst of radiation before vanishing entirely. The last sigh of a black hole may light the universe for an instant before fading into the endless dark. What would remain after the last black hole's evaporation is a universe stripped of complexity, the last great strongholds of gravity dissolved, the last repositories of memory erased. Even information itself, once debated as trapped within horizons, would either be released in faint radiation or vanish into riddles no one is left to untangle. The poetry of this vision is both majestic and desolate. Black holes, born from the deaths of stars, nurtured in the hearts of galaxies, will outlive nearly everything. They will sit as dark monarchs over an increasingly barren cosmos, keeping their silence for longer than stars could dream of shining. But their reign is finite. Even kings of gravity must bow to time. To think of the universe's final act is to think of black holes as the closing performers. They are the last great drama, the final long echoes of a cosmos once vibrant with creation. And when they too are gone, what remains is only the whisper of photons and neutrinos stretched across endless distances, their energy so dilute it barely registers as real. The universe, which once birthed galaxies of unimaginable brilliance, will end not with a blaze of glory, but with the quiet extinguishing of its last and darkest lights. The frontier of gravity, once absolute, becomes the last candle to burn and then is gone. If black holes whisper across unimaginable time, there is another, more intimate clock that might be ticking beneath the surface of matter itself, the potential instability of protons. At first glance, protons appear eternal. They are the sturdy building blocks of atoms, the anchors of chemistry, the particles that persist when electrons vanish and neutrons decay. Without them, the familiar matter of stars, planets, and living beings could not exist. Yet in the deeper frameworks of particle physics, the permanence of the proton is not guaranteed. Many grand unified theories, GUTs, attempts to merge the strong, weak, and electromagnetic forces into a single description predict that protons should eventually decay. Not in millions or billions of years, but over timescales so vast that entire galaxies could rise and fall before a single proton per atom has split. Typical predictions place the half-life at 10 to the power of 34 to 10 to the power of 36 years or longer. If such decay occurs, the universe's endgame shifts dramatically, for even the seemingly indestructible scaffolding of matter would one day crumble into radiation. Experiments have sought to glimpse this process. Deep beneath mountains and oceans, enormous detectors have been built to watch for the faintest trace of proton decay. Japan's Super Kamiokande, a tank of 50,000 tons of pure water surrounded by sensitive photomultiplier tubes, has been staring into silence for decades. Future upgrades, such as Hyper Kamiokande, promise even greater reach. So far, no proton has been seen to decay. The silence itself is meaningful. It tells us that if decay exists, it must be slower than many theories had hoped, pushing the half-life beyond 10 to the power of 34 years. But in the scale of eternity, even that is not safety. If protons eventually fall apart, then black dwarfs, the remnants of once luminous stars, will not simply fade, but dissolve. Neutron stars, despite their density, will also succumb. Planets and rocky remnants will vanish into cascades of photons and lighter particles. The cosmos will move inexorably toward a bath of radiation, hastening the smoothing of entropy. There is something profoundly unsettling in this vision. It suggests that nothing material is permanent, that the particles we think of as the bedrock of reality are only temporary arrangements. The stones of Earth, the bones of stars, the very atoms in our blood, all are structures waiting to disintegrate in silence, if the laws of physics demand it. Yet there is also a paradoxical beauty. Proton decay, if it exists, would mean that the universe is not frozen in eternal stasis, but participates in the same cycle of transformation as all living things. Stars burn, galaxies evolve, and perhaps even matter itself eventually returns to energy, completing a loop that began in the furnace of the Big Bang. In the far future universe, where time is measured not in billions but in quintillions of years, the fate of the proton may decide the tempo of the end. If stable, matter will persist in inert lumps, delaying entropy's silence. If unstable, the decay of protons will accelerate the descent into equilibrium, leaving behind nothing but radiation. And so, deep inside the nuclei of every atom, the universe hides another possible ending, a secret countdown whose numbers are written not in calendars or clocks, but in the equations of unification equations we are only beginning to glimpse. If proton decay sketches the slow dissolution of matter, the Big Rip imagines an ending far more violent, a finale written not in patience, but in frenzy. It emerges from one crucial possibility: that the pressure of dark energy is not simply equal to a cosmological constant, but stronger, stranger, more extreme. In cosmology, the behavior of dark energy is described by its equation of state parameter, W, the ratio of its pressure to its energy density. For a cosmological constant, W equals 1, a steady value that stretches space at a constant rate. But if W dips below 1 into what physicists call phantom energy, the expansion of the universe accelerates not gently, but catastrophically. The effect compounds itself. As the universe expands, the energy density of phantom energy increases, fueling still faster expansion. The result is an unstoppable spiral toward disintegration. The Big Rip begins subtly. Galaxies drift apart faster than their gravity can hold them together. Then, as time races forward, solar systems themselves are unbound. Planets spiral into darkness as their stars slip away. Next, stars are torn apart, shredded into plasma by the relentless stretching of space-time. Eventually, the scale of destruction descends to molecules, atoms, even nuclei. The very bonds that hold protons and neutrons together cannot withstand the strain. The universe does not simply fade, it is ripped to shreds, down to its smallest scales. The timeline depends on how far W slips below 1. If just slightly, the Big Rip might arrive in tens of billions of years. If more severe, it could unfold much sooner. Observations from supernovae, cosmic microwave background maps, and galaxy surveys currently suggest W is very close to 1, with no strong evidence yet of phantom behavior. Still, the possibility cannot be excluded, and so the spectre of a rip hovers in the space of uncertainty. The image is haunting. Unlike heat death, which offers a long twilight of cooling, the Big Rip is a storm, a crescendo that shatters the universe in a finite future. It is an ending of drama, not melancholy, a violent tearing rather than a quiet dissolution. For those who ponder it, the thought is chilling. The very fabric of reality could become unstable, stretching itself apart until nothing remains bound. The Big Rip reveals the precariousness of cosmic law. A tiny shift in the properties of dark energy transforms the universe's destiny from an endless decline into an abrupt annihilation. It reminds us how delicately existence depends on parameters we barely understand, numbers that could tip one way or another with consequences beyond comprehension. And yet, there is also poetry in the Rip. To imagine the cosmos tearing itself apart is to glimpse the wildness of space-time, its capacity not only to cradle galaxies but to destroy them. It is a vision of impermanence, elevated to the highest scale, not only stars and worlds, but the very scaffolding of reality itself torn away. In the end, whether phantom energy is real or not, The Big Rip stands as a symbol of possibility, a reminder that the universe's future is not guaranteed, and that the laws we measure today may hold within them the seeds of tomorrow's cataclysm. There was a time when the Big Crunch stood as the most natural ending for the cosmos. If the universe had expanded from a hot, dense beginning, why should it not one day reverse? Gravity, after all, was the great binder. Given enough matter, enough density, the outward flight of galaxies could be slowed, halted, and turned inward. The future would then collapse into fire, a mirror of the Big Bang in reverse, the entire cosmos converging into a final singularity, a cosmic implosion. This vision carried a certain symmetry. The universe, born in a fiery creation, would close in a fiery annihilation, a grand cycle of beginning and end. For much of the 20th century, cosmologists debated whether the cosmos contained enough matter to achieve this reversal. The critical density, the threshold at which gravity could halt expansion, became a number of obsession. If the density of matter was above this line, collapse was inevitable. If below, eternal expansion was assured. Early measurements were uncertain. Galaxies' motions, clusters' masses, the distribution of matter all hinted that the universe might be close to this critical balance. The possibility of a crunch was real. Many theorists even preferred it. A collapsing universe seemed philosophically satisfying, a way to avoid an eternity of futility, offering instead a closed loop of creation and destruction. But as measurements improved, the dream of a crunch began to fade. Dark matter, though abundant, was not enough to tip the scales. And then came the revelation of dark energy, an invisible pressure that not only countered gravity, but accelerated expansion. With that discovery, the Big Crunch was largely exiled from probability. If dark energy is constant or growing, collapse becomes impossible. Instead of returning inward, galaxies recede ever faster, forever beyond reach. Still, the crunch remains a ghost at the edge of cosmology. Some models of evolving dark energy allow for its strength to weaken over time. Should dark energy decay or reverse sign, the tug of gravity might reclaim dominance. The cosmos could slow, halt, and fold inward, triggering a catastrophic implosion. In speculative theories, this collapse might even spark a bounce, igniting a new Big Bang, birthing a new cosmos from the ashes of the old. The idea is haunting, the entire sky drawn back upon itself, galaxies accelerating inward, the fabric of space contracting, temperatures soaring as everything rushes toward a final singularity. It is a vision of fire, of compression, of the cosmos devouring itself in its last act. Philosophically, the Big Crunch still holds allure. It offers closure, symmetry, a circle of existence that neither fades into cold emptiness nor rips itself apart in violence. It imagines the universe as a heartbeat, expanding and contracting, a rhythm echoing across eternity. Though current evidence makes it unlikely, it remains a poetic counterpoint to the bleakness of endless acceleration. And so, the Big Crunch lingers as both a memory of cosmology's past and a reminder of its fragility. For the universe's fate rests on quantities still uncertain, and a change in their measure could alter the script entirely. The sky might be racing outward today, but in the depths of future physics, the possibility of reversal still hums, faint but persistent. If the Big Crunch imagines a single collapse, then the dream of cycles and rebounds paints the cosmos as eternal rhythm, not a line from birth to death, but a loop of beginnings that never truly end. Here, the universe does not die once, but transforms endlessly, each conclusion becoming the seed of another dawn. Such ideas are ancient. In mythologies across cultures, the cosmos was often imagined as cyclical, worlds destroyed and reborn, time repeating itself in great ages. Modern physics, reaching beyond myth, has occasionally echoed this rhythm. Could the Big Bang itself have been the rebound of a previous collapse? Could expansion and contraction alternate like a cosmic heartbeat? One such vision is the cyclic model, where the universe undergoes a series of expansions and contractions. In older versions, gravity alone was the engine. The cosmos expands, slows, collapses, and explodes again. But with the discovery of dark energy, newer models emerged. Some theories in string cosmology propose that our universe exists as a three-dimensional membrane, or brane, floating in higher dimensional space. Collisions between branes might trigger repeated Big Bangs, setting off cycles that extend indefinitely into the past and future. Another version, the ekpyrotic scenario, imagines a slow, smoothing contraction before the bounce. Rather than a chaotic collapse, the universe would compress gently, ironing out irregularities, then explode into a new cycle of expansion. In such models, the cosmos avoids singularities altogether. There is no end in the absolute sense, only transitions from one cycle to the next, from one universe to another. Evidence for such ideas remains elusive. Observations of the cosmic microwave background have searched for imprints, scars, or signatures left by previous cycles, but so far the sky has revealed no clear trace. Dark energy's apparent constancy also complicates the dream, suggesting that expansion may accelerate forever rather than turn back. Yet theorists continue to explore these possibilities, for they offer a way to reconcile endings with beginnings. The philosophical allure is undeniable. A cyclic universe offers a story without finality, where entropy itself might reset, where memory and meaning could return in new forms. Death, in this vision, is never absolute. It is transformation, a turning of the wheel, a chance for new stories to unfold. And yet, there is unease. If cycles truly repeat, do they bring back the same histories, the same lives, the same stars? Would we live again, identically, endlessly? Or would each cycle diverge, birthing different universes, different structures, different stories? The thought is as haunting as it is comforting. Eternity not as endless silence, but as endless variation. The cyclic cosmos stands as a counterpoint to the finality of heat death and the violence of the Big Rip. It suggests that the universe may never truly end, but may instead breathe forever, a cosmic lung inhaling and exhaling across timeless eons. Among the possible endings of the universe, few are as unsettling as the threat that lurks in the equations of quantum fields. The idea that our reality itself may be metastable. Unlike heat death or the Big Rip, which are written in the language of expansion and gravity, this fate is hidden in the very vacuum of space, the invisible stage on which all physics unfolds. The discovery of the Higgs boson in 2012 at CERN's Large Hadron Collider was hailed as a triumph, the final missing piece of the standard model of particle physics. Yet the mass of the Higgs, measured at around 125 gigaelectronvolts, carries a haunting implication. Combined with the mass of the top quark, it suggests that our universe's vacuum, the field value that defines reality as we know it, may not be in its absolute lowest energy state. Instead, we may live in a false vacuum, a precarious plateau in a broader energy landscape. If this is true, then hidden somewhere beyond our current reach lies a deeper valley, a state of lower energy that the universe could, in principle, fall into. The danger is not merely abstract. Should quantum tunneling trigger a transition to this true vacuum, the laws of physics themselves would be rewritten. The Higgs field gives mass to particles. A shift in its value would alter the very fabric of matter. Atoms might disintegrate, chemistry would be impossible, and the familiar forces might take forms alien and unrecognizable. This process, called vacuum decay, would not unfold gently. A bubble of true vacuum could nucleate anywhere in the cosmos, perhaps triggered by quantum fluctuations or extreme conditions near black holes. Once formed, it would expand at the speed of light, devouring everything in its path. Stars, galaxies, planets, even space-time itself would be consumed, leaving behind a sterile, alien void. There would be no warning, no survival, no witness. What makes this possibility so chilling is its silence. Unlike a big crunch or rip, which play out over cosmic timescales, vacuum decay would be instantaneous on a local scale. One moment, the universe would be as it is. The next, it would not exist in any recognizable sense. The end would come without announcement, and it could already be racing toward us, unseen. And yet, the mathematics of metastability is subtle. The lifetime of our vacuum, calculated from quantum field theory, is staggeringly long, trillions upon trillions of times the current age of the universe. It may be effectively eternal, or it may not. The fact that we are here at all means it has lasted long enough, but nothing guarantees its permanence. This vision turns the end of the universe from a distant astrophysical process into a quantum possibility woven into the present moment. It reveals the precariousness of existence. Not only stars and galaxies, but the very ground of reality may be temporary. Philosophically, metastability is a mirror. It shows us how fragile permanence can be, how existence itself might rest on a plateau of chance. To live in such a universe is to live with the knowledge that the void beneath our feet is not guaranteed, that the cosmos could, at any instant, slip into silence. And yet, it is precisely this fragility that makes our present existence meaningful. The precarious balance of the Higgs field is what allows atoms, molecules, and life to exist at all. We live suspended in a delicate state, perhaps not absolute, but sufficient to carry the universe through its great arc of time. The shadow of metastability, haunting though it is, reminds us that reality is not given, but gifted, a fragile flame flickering in the dark. If the universe does rest in a false vacuum, then its demise would not be slow and quiet, but sudden, absolute, and merciless. To imagine this fate is to picture a cosmos undone by a single bubble, a tiny region where reality itself has slipped into a deeper state of energy. The physics of such a transition was worked out by Sidney Coleman and Frank DeLucia in the late 20th century. They described how a bubble of true vacuum might form within a metastable false vacuum born from quantum tunneling. At first, the bubble would be microscopic, but once created, it would expand at the speed of light, its surface an unstoppable wall, rewriting space-time. Inside the bubble, the constants of nature would be different. The rules of chemistry, of matter, of life would be erased. No structure could survive the transition. What makes this vision chilling is its inevitability. If the vacuum is metastable, then the formation of such a bubble is not a question of if, but when, and when it comes, there is no alarm, no approach, no anticipation. The bubble wall advances at light speed, so the instant one becomes aware of it is the instant one ceases to exist. It is an apocalypse that arrives not as fire or collapse, but as instantaneous oblivion. The scale of destruction is not limited to stars and galaxies. It is deeper than that. The very fields that shape the particles of matter, the Higgs, the electromagnetic, the nuclear forces are altered. An electron may no longer exist as an electron. A proton may dissolve instantly. The periodic table, the chemistry of life, the stability of atoms, all vanish, rewritten into forms that are unrecognizable or into nothing at all. Yet, the mathematics offers both terror and comfort. The predicted lifetime of our vacuum, given the measured values of the Higgs boson and top quark, is vastly longer than the age of the universe. If decay is possible, it may not happen for trillions of years, or longer still. In that sense, it is a possibility that hangs like a sword above eternity, but one that may never fall during any conceivable cosmic epoch. Still, the thought lingers. We live in a universe where the ground state of reality may not be the ground at all. Our existence could be like a candle burning on a thin film of ice, fragile against the depths below. The knowledge reshapes our relationship to permanence, revealing that even the most fundamental laws we know may not be final. Philosophers once asked whether the universe would end in fire or ice. Vacuum decay suggests a third option, a vanishing, a silent rewriting of existence so thorough that even the question itself disappears. It is the most radical of endings, one that annihilates not only structures of matter, but the very definitions of physics, causality, and time. And yet, within this unsettling possibility lies a peculiar kind of peace. If a vacuum bubble were to appear and sweep across us, we would never see it coming. There would be no suffering, no lingering twilight. One moment the cosmos would exist, the next it would not. An end as swift as the flick of a light. This, too, is a kind of ending written into the spectrum of possibilities. A universe that dreamed itself into galaxies, stars, and life could also dream itself away in an instant, not with a scream, but with a silence too complete for even memory to escape. Long before the discovery of dark energy, cosmologists had already learned to live with a force of astonishing strangeness. Cosmic inflation, born from the puzzles of the early universe. Inflation proposed that in the first fractions of a second after the Big Bang, space itself expanded faster than light, smoothing out irregularities, flattening geometry, and scattering quantum fluctuations that later grew into galaxies. It was an audacious idea, but one that explained mysteries no other theory could touch: why the cosmos looks so uniform on large scales, why its curvature is so close to flat, and why structure exists at all. Inflation, however, came with an aftertaste, the possibility that it never fully ended. If the inflaton field, the hypothetical energy driving this expansion, decays unevenly, then some regions stop inflating while others continue. This leads to eternal inflation, a patchwork cosmos where bubbles of normal universe like ours form within an ever-growing inflating background. Each bubble might host its own laws of physics, its own constants, its own possibilities. Together, they form what some physicists call the multiverse. In this vision, our universe's fate is not singular, but plural. Even as our own bubble drifts toward heat death, Big Rip, or vacuum decay, elsewhere new bubbles are still forming, each beginning its own expansion. Endings become local, not global. The cosmos as a whole never truly ends. It endlessly buds, endlessly creates. But eternal inflation carries profound questions. If the multiverse exists, then what we call the universe is only one island among countless others. Its fate may matter only within its shores. Heat death here is irrelevant there. A big rip here may coincide with a new birth somewhere else. The end of our universe is not the end of existence, but the turning of one page in an infinite, unreadable book. The theory also forces us to reconsider dark energy. Could the acceleration we observe today be a cousin of the inflationary force that once drove the early cosmos? Perhaps the same physics that flung the universe into being still whispers at its edges, steering its long future. If so, dark energy might be a faint echo of inflation, an aftershock of creation that never entirely ceased. The unsettling consequence is that our cosmic fate may not be unique. There could be universes where dark energy behaves differently, some collapsing, some tearing apart, some cycling endlessly. Ours is simply one thread in a vast tapestry, one experiment among many. The concept of the end becomes ambiguous, dependent on where one stands in the multiverse. And yet, for all its abstraction, eternal inflation connects intimately with our own mortality. It suggests that endings are relative, that what feels like finality from within may be only transition from a broader perspective. Just as stars die to give birth to elements, and galaxies collide to shape new structures, so too may universes die to allow others to rise. Still, evidence remains elusive. The multiverse lies beyond direct observation, perhaps forever hidden. Some call it philosophy rather than physics, speculation rather than science. And yet, inflation itself, once equally audacious, has left fingerprints in the cosmic microwave background. Perhaps, one day, echoes of eternal inflation will reveal themselves too. If so, the end of our universe will not be a solitary silence, but one note in an endless chorus, a fading bubble in a froth that never ceases to boil. If eternal inflation paints a cosmos of infinite variety, our own universe is constrained by something more sobering: cosmological horizons. These are the boundaries of what can ever be seen or known, not because of technological limits, but because of the very nature of space-time itself. In an accelerating universe, there are places we can never reach, messages we will never receive, galaxies that will slip permanently beyond our sight. This horizon is not like the edge of a cliff, but more like the horizon at sea, a limit of vision that recedes as you move, yet always exists. In cosmology, the event horizon is the ultimate boundary, the distance beyond which events can never affect us, no matter how long we wait. As expansion accelerates, galaxies beyond this horizon are lost forever. Their light, stretched by expansion, will never reach us. In the deep future, even neighboring galaxies will vanish into darkness, leaving each island universe alone, unaware of the greater web that once bound them. The consequences are profound. A horizon means that information itself is lost to us. The cosmos we see is not the cosmos as a whole, but only a fading fragment. Beyond the horizon, space continues, but for us it might as well not exist. The story of the universe, as told from our vantage point, becomes partial, a narrative cut off from its larger context. This introduces a strange tension. The universe may contain an infinity of galaxies, but for any observer, there will come a time when the night sky contains only the remnants of their local cluster. In our case, perhaps only the merged galaxy of the Milky Way and Andromeda will remain visible, adrift in silent darkness. Cosmology, as a science, will become impossible. The sky itself will erase its evidence. Future astronomers, if any remain, will live in a universe that conceals its true history, a cosmic stage stripped of context. Philosophically, horizons raise unsettling questions about memory and meaning. If information can slip beyond reach, what does it mean to say the universe exists as a whole? If reality is fractured by horizons, then knowledge is always local, bounded, incomplete. The dream of understanding everything dissolves into the humility of knowing only what the horizon permits. There is also the enigma of information loss. In black hole physics, the question of whether information swallowed by horizons is truly destroyed has haunted theorists for decades. Now, cosmology echoes that puzzle on the grandest scale. When galaxies vanish beyond the cosmic event horizon, is their information gone forever? Does the universe forget them? Or is the memory hidden in ways we cannot yet grasp? As acceleration continues, horizons will multiply their silence. Even the cosmic microwave background, once the great afterglow of creation, will be stretched until its photons grow so faint and so long in wavelength that they are undetectable. The very evidence of the Big Bang will vanish. The universe will not only age, it will erase its own origin story. To live in a universe with horizons is to accept impermanence not just in matter, but in knowledge. Our window onto the cosmos is temporary, a gift of timing. We are fortunate to exist in an epoch when the sky still reveals its vastness, when the echoes of the Big Bang are still audible, when galaxies still shine. In the deep future, those windows will close. And so, horizons are not merely scientific curiosities, they are metaphors of loss, reminders that even knowledge is finite, that even memory fades, that the universe itself places boundaries on what can be seen, known, and remembered. The end of the universe, in this sense, is not only physical, it is also an end of vision. From horizons and their silence arises another paradox, one that unsettles the very logic of probability, the possibility of Boltzmann brains. These are hypothetical observers, minds without bodies, thought without history arising not from evolution or stars, but from random fluctuations in a near-empty universe. The idea begins with entropy. In an eternal heat death, where the cosmos drifts at maximum disorder, rare fluctuations are still possible. Given infinite time, particles might occasionally arrange themselves into unlikely structures. Most of the time, the fluctuation would be trivial, a cluster of atoms here, a brief energy spike there. But sometimes, unimaginably rarely, the fluctuation might be vast enough to form something complex. A galaxy, a planet, or, in the strangest possibility, a conscious brain. Such a brain would blink into existence, complete with false memories, illusory perceptions, and the sensation of living a life it never truly lived. It would exist for a fleeting instant before dissolving back into the void. And yet, if the universe lasts forever in a heat-death state, the odds eventually favor Boltzmann brains over evolved beings like us. In the arithmetic of infinity, it is far more probable for a single brain to fluctuate into existence than for an entire universe to arise naturally and sustain billions of years of evolution. This paradox shakes cosmology at its core. If the universe's ultimate fate is an endless equilibrium, then statistically, most observers should be Boltzmann brains, not evolved life forms. But if that is the case, why do we see a coherent, structured universe with history and order? Why do we remember a past that is consistent and continuous, rather than fragmented illusions? Physicists recoil at the thought, not only for its absurdity but for its challenge to reason itself. A theory that predicts Boltzmann brains more likely than genuine observers is considered unacceptable. It suggests the theory itself is flawed or incomplete. The cosmos cannot be dominated by such solipsistic accidents, or else all science collapses into doubt. And yet, the possibility lingers. Tethered to the mathematics of entropy and eternity, it forces cosmologists to ask whether heat death is truly the end, or whether the rules of probability break down in such extremes. It challenges our understanding of observation, identity, and meaning. Philosophically, Boltzmann brains are mirrors of existential fear. They embody the dread that reality may be an illusion, that memory is unreliable, that our sense of continuity could dissolve into chaos at any moment. They remind us that consciousness is fragile, precarious, and deeply bound to the order of the cosmos. For now, the paradox remains unresolved. The hope is that deeper physics, whether in quantum gravity, multiverse theory, or evolving dark energy, will provide an escape, a way to ensure that structured universes with long histories dominate over isolated fluctuations. But until then, the Boltzmann brain hovers in our imagination like a ghost, an observer in the dark, asking whether we ourselves are anything more than a fleeting fluctuation in the silence of eternity. If the thought of Boltzmann brains unsettles reason, the question of time and recurrence unsettles existence itself. For time is not merely the measure of change, but the stage upon which endings unfold. If the universe is endless, what does it mean to say that it ends? And if entropy rules, does time itself wither when change ceases? The Poincaré recurrence theorem whispers one answer. In a finite system, given enough time, every possible configuration will eventually repeat. In principle, a universe that drifts long enough could cycle through its states, returning not only to order, but even to patterns resembling its past. The molecules that once formed a star might, after inconceivable aeons, assemble again into something star-like. The atoms that once made a human might, against all probability, reconstitute into a fleeting double. In this sense, endings are never absolute, only pauses before improbable repetition. But the scales involved are monstrous. The recurrence time for the universe, if it is finite, dwarfs even the lifespan of black holes or proton decay. It is a time so vast that it defies imagination, a number beyond numbers, written in exponential towers. And even then, recurrence is not certainty, only possibility. It is a mathematical ghost, not a practical prophecy. The idea of recurrence forces us to rethink the meaning of an end. If the universe repeats, does it truly die, or does it merely slumber, awaiting another roll of the cosmic dice? Does recurrence bring back the same histories, the same people, the same galaxies, or only echoes, distorted variations, endless copies, none of which know they are copies? Then there is the question of de sitter recurrences in an eternally inflating or accelerating universe. If space is dominated by dark energy, horizons set finite limits on entropy. Over incomprehensible spans, fluctuations could reset conditions, birthing new pockets of apparent order, perhaps even new big bangs within the silence of heat death. In this sense, the end is only a phase, a lull, before another round of creation. But these possibilities carry with them unsettling paradoxes. If time is endless and recurrence inevitable, then every possible history must play out, not once, but infinitely. Every life, every moment, every thought repeated without number, mirrored across eternity. For some, this is a vision of immortality, a way to cheat finality. For others, it is a nightmare of eternal repetition, where even endings are denied. And yet, there is another possibility, that time itself is not eternal, but emergent. Some theories of quantum gravity suggest that time may be a property of change, not a backdrop upon which change occurs. If so, then in heat death, when change ceases, time may end too. The universe would not recur because there would be no later in which recurrence could unfold. The arrow of time, born from entropy, would vanish when entropy reaches its maximum. Thus, the question of recurrence is not only about physics, but about philosophy. It forces us to ask whether eternity is real, whether endings are final, and whether time is a line, a circle, or an illusion. It reminds us that in seeking the universe's end, we are really seeking the meaning of time itself and whether there can ever be such a thing as a last moment. With horizons limiting what can be known and entropy charting the long decline, the only way forward is measurement sharper, deeper, more precise measurements of the universe's pulse. The fate of the cosmos depends on the properties of dark energy, and to pin them down requires new tools, new eyes, new catalogues of light. The universe is speaking through the flicker of its distant explosions, and astronomers are listening. The first great effort was the discovery of acceleration through Type Ia supernovae, those brilliant thermonuclear detonations that outshine entire galaxies. They are reliable beacons, their intrinsic brightness known, their distances measurable by comparing what we expect with what we observe. But the surveys of the 1,990 seconds, while groundbreaking, were limited in scope. To refine the story of cosmic destiny, the next generation of observatories is pushing deeper. The Dark Energy Survey, DES, completed in 2019, charted hundreds of millions of galaxies and thousands of supernovae, mapping the expansion with greater clarity than ever before. Its successor projects carry the torch further. The Dark Energy Spectroscopic Instrument, DESI, mounted on the Mail Telescope in Arizona, is measuring the light of tens of millions of galaxies and quasars, constructing a three-dimensional map of the universe on scales never before attempted. With DESI, cosmologists hope to trace the subtle variations of the expansion rate across cosmic history to see whether dark energy evolves over time or remains constant. Then there is the Vera C. Rubin Observatory in Chile, preparing to launch the Legacy Survey of Space and Time, LSST. Over a decade, LSST will image the sky every few nights, capturing billions of galaxies, countless supernovae, and the flickering dance of the transient sky. It will not only measure dark energy's effect on cosmic geometry, but also watch for new surprises, new anomalies that may hint at physics beyond our models. Together, these surveys act as a kind of cosmic cardiogram, recording the heartbeat of expansion. They seek to measure the equation of state parameter, W, with unprecedented precision. Is it exactly, 1, the hallmark of a cosmological constant? Or is it shifting, drifting with time, suggesting a dynamic field like quintessence? Even tiny deviations could determine whether the universe ends in heat, death, rip, or collapse. This is science as prophecy, not in the mystical sense, but in the empirical one. Prediction grounded in data, fate sketched from light curves and redshifts. Each supernova observed, each galaxy mapped, adds another stitch to the fabric of the universe's story. And yet, the work is not only technical, it is profoundly human. To watch the death of a star halfway across the universe, and to measure in its brightness the acceleration of all existence, is to participate in an act of extraordinary vision. It is to see not only what was, but what may be. The tools are instruments of physics, but their aim is existential, to know how the cosmos ends. The future of cosmology rests on these beacons. As they flicker into detectors and cameras, they whisper of the universe's destiny, carrying messages across billions of years. From them, we will learn whether the cosmos drifts gently into silence, tears itself apart, or collapses into fire. And so, the night sky becomes not just a backdrop of stars, but a library of endings waiting to be read. If supernovae provide the candles by which to measure distance, then the cosmic web itself offers the great scaffold upon which fate is written. Galaxies are not scattered randomly, but form vast filaments, clusters, and voids, a three-dimensional tapestry stretching across the observable universe. Within this structure lies another ruler, another voice of expansion, the imprint of ancient sound waves, frozen in space. These are the baryon acoustic oscillations, BAO, the faint ripples left from pressure waves in the hot plasma of the early universe. Before atoms formed, photons and matter were tightly coupled, creating oscillations much like sound traveling through air. When the universe cooled enough for atoms to form, the waves froze, leaving a preferred scale about 500 million light-years imprinted in the clustering of galaxies. By measuring this scale at different epochs, cosmologists can reconstruct how expansion has unfolded, as if tracing the beats of the cosmic heart. Modern surveys, like the Sloan Digital Sky Survey, SDSS, and the ongoing DESI project, map millions of galaxies to measure these ripples with exquisite precision. Combined with weak gravitational lensing, the subtle bending of light as it passes through large-scale structures, they provide independent checks on dark energy's behavior. If galaxies cluster less than expected, or if lensing patterns deviate from predictions, it could mean dark energy is evolving, or that general relativity itself is incomplete on cosmic scales. The cosmic web also reveals another truth. Structure is fragile. Gravity pulls galaxies together, weaving filaments over billions of years. But as expansion accelerates, this growth slows, then halts. In the far future, dark energy will stretch the web until filaments disconnect, clusters dissolve, and each galaxy drifts alone. By mapping how the web evolves, cosmologists can forecast this unraveling, predicting how long the cosmic network will endure. The tools for this work are immense. DESI's spectrographs can measure the redshifts of 5,000 galaxies at once. The upcoming Rubin Observatory's LSST will catalogue billions of galaxies, charting the web in motion. Space missions like Euclid and Nancy Grace Roman Space Telescope will add still greater depth, probing weak lensing with clarity unachievable from Earth. Together, these efforts form a global collaboration, an unprecedented attempt to measure fate itself. And in the data, hints emerge. The cosmic web seems to confirm a universe dominated by dark energy, with W close to 1. But subtle tensions, small discrepancies between different methods, keep the door open to surprises. Perhaps the web is whispering of new physics, or perhaps the noise will fade with better measurements. In either case, the cosmic web is the stage upon which destiny is measured. Philosophically, there is poetry in this pursuit. The same filaments that cradle galaxies and foster stars also serve as rulers of the end. The web is both cradle and clock, both architecture and prophecy. To study it is to recognize that structure itself contains its dissolution, that the fabric which binds also foretells its unbinding. The heartbeat of the cosmic web is faint, but it is steady, and in its pulse lies the answer to whether the universe will drift, collapse, or tear a fate measured not in stars, but in the spaces between them. If galaxies and the cosmic web sketch the scaffolding of expansion, then the cosmic microwave background, that faint, frozen afterglow from the universe's birth, provides the most ancient record of all. It is the oldest light we can see, released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. This radiation fills the sky in every direction, a whisper of origin encoded in microwaves, stretched by billions of years of expansion. From COBE to WMAP to Planck, satellites have turned this faint afterglow into a cosmic map. The mottled patches of slightly warmer and cooler regions tell us about density variations in the early universe, the seeds from which galaxies and clusters would later grow. But these patterns also contain deeper messages, subtle harmonics that reveal the very composition and fate of the cosmos. The spectrum of the CMB is astonishingly close to perfect blackbody radiation, a relic of a universe once in near thermal equilibrium. Yet within its ripples, cosmologists find fingerprints of fundamental parameters: the density of baryons, the abundance of dark matter, the geometry of space, and the strength of dark energy. Planck's exquisite measurements confirmed with near certainty that the cosmos is flat on large scales, a result that narrows the range of its possible destinies. But the CMB speaks also to the future. By comparing its ancient imprints with today's cosmic structures, physicists can measure how expansion has unfolded and whether dark energy has remained constant. Slight anomalies in the CMB, odd alignments, unexpected cold spots, tensions with galaxy surveys hint that the universe may not be as simple as LCDM, the standard model of cosmology, suggests. These tensions are small, yet persistent, keeping alive the question of whether new physics might be at play. Future missions will refine this cosmic message still further. The Simons Observatory in Chile and the planned CMB-S4 project aim to measure polarization patterns with exquisite precision, searching for traces of primordial gravitational waves from inflation. Such observations would not only illuminate the beginning, but also constrain the late-time fate by testing the nature of dark energy neutrino masses, and the possibility of evolving fields. There is something haunting in this, that the faint afterglow of the first fireball, stretched to invisibility, still speaks across nearly 14 billion years, still contains within it clues to the last moments of the universe. The CMB is both prologue and prophecy, a relic of the cosmos's youth that guides our understanding of its old age. Philosophically, it is as though the universe left a message for itself, carved into radiation at its birth, waiting for minds to evolve billions of years later to read it. That message, encoded in the faintest of photons, tells us not only where we came from, but where we are going. The afterglow is not just memory, it is foresight, a bridge between the first light and the last. In the end, the spectrum is a kind of scripture, written not in words but in microwaves, telling of creation, structure, and destiny. And though it will one day fade into undetectable wavelengths as expansion stretches it beyond reach, we live in a fleeting age when it is still audible, the universe's own testament to its beginning and its end. If the cosmic microwave background speaks of the universe's infancy, then gravitational waves whisper of its ongoing symphony, the low, deep tones of spacetime itself, vibrating as massive bodies move. Unlike light, which can be absorbed or scattered, gravitational waves pass almost unhindered through the cosmos, carrying with them messages from epochs and regions unreachable by photons, and in their faint tremors may lie clues to the universe's ultimate fate. The first detection came in 2015, when the twin detectors of LIGO in the United States measured the ripple from two colliding black holes over 1 billion light-years away. It was a triumph. Einstein's century-old prediction finally heard. Since then, LIGO, Virgo in Italy, and Kagra in Japan have recorded dozens of such signals, the mergers of black holes and neutron stars, cataclysms that shake the geometry of spacetime itself. On one level, these detections are intimate stories, the deaths of stars, the formation of black holes, but on another, they are windows into the deep future. Gravitational waves reveal the population of compact objects, the relics that will dominate when stars have burned out. By measuring their abundance, their masses, their mergers, we trace the demographics of the last structures the universe will know. In the far future, when galaxies fade, it is black holes that will remain, circling one another in darkness, colliding in silence. Each collision sends out a final shiver of spacetime, a ripple that expands outward forever. The universe's last fireworks may not be visible as light, but as gravity's murmur, a soundless music played in the fabric of being. But gravitational waves also probe the cosmos itself. Their travel across billions of light-years makes them sensitive to the expansion of space. By comparing their measured strength with electromagnetic signals, cosmologists can test the rate of expansion and refine the equation of state of dark energy. Gravitational waves thus become standard sirens, complementing the supernova candles and the BAO rulers. They are new instruments in the orchestra of fate measurement. Future missions promise even more profound revelations. LISA, Laser Interferometer Space Antenna, planned for the 2030 seconds, will place detectors in orbit around the Sun, capable of sensing waves from supermassive black hole mergers and even relic signals from the early universe. Such signals could reveal whether inflation left behind a primordial gravitational wave background, a fossil of creation itself. And by tracing how waves stretch as they travel through an accelerating cosmos, LISA and its successors may constrain dark energy with unprecedented precision. The poetry of gravitational waves is unique. They are not light, not matter, but pure geometry, the universe speaking in the rhythm of its own curvature. To listen to them is to hear the cosmos not as image, but as vibration, not as appearance, but as pulse. In the long night of the far future, when light itself fades, It may be these ripples that outlast the stars, a final echo of motion in an ever-silent sky. Philosophically, gravitational waves remind us that endings are not always visible. The universe may dim, but it will still hum. The merging of black holes, the collapse of remnants, the trembling of space-time, these are the quiet verses of the last poem. In them, the fate of the cosmos is written not in light, but in the very breath of space-time itself. Beyond stars, beyond galaxies, beyond even black holes, there remains another cast of characters, faint, elusive, almost invisible. These are the relic particles, the whispers of physics that may shape the very last pages of the universe's story. Neutrinos, axions, and other dark sector candidates. They are the quietest presences in the cosmic symphony, yet over eternity, even whispers accumulate into destiny. Neutrinos were born in the first seconds of the Big Bang, a flood of nearly massless particles racing outward at nearly the speed of light. Trillions stream through every square centimeter of our bodies each second, yet they barely touch us, ghost-like in their aloofness. For decades they were thought to be massless, but experiments have revealed that they carry a tiny, non-zero mass enough to influence cosmic evolution. In the early universe, neutrinos slowed the growth of structure, leaving imprints detectable in the cosmic microwave background and the clustering of galaxies. In the deep future, their faint presence will persist even as stars and atoms vanish, a relic sea of particles adrift in an expanding void. Then there are axions, hypothetical particles proposed to solve a puzzle in the laws of the strong nuclear force. If they exist, they could be a component of dark matter, adding to the hidden scaffolding of the cosmos. Unlike massive dark matter particles, axions would be feather-light, forming vast condensates that subtly shape cosmic structure. Over time, they might alter the cooling of stars, the behavior of compact remnants, or the long-term thermal balance of the universe. Other dark sector candidates lurk in theory: sterile neutrinos, weakly interacting massive particles, fields that do not shine but exert influence. Each could play a role in the cooling, clustering, or dissolution of the cosmos. Though they act invisibly, their cumulative effect stretches across aeons. Like unseen hands, they tug at the tempo of fate. In the laboratory, efforts to detect these faint players continue. Giant underground detectors like Super Kamiokande and its successors search for rare neutrino interactions. Axion haloscopes, resonant cavities tuned to pick up their subtle signals, hum in radio silence, waiting for a faint trace. Particle accelerators push boundaries, probing the shadows of the standard model for new clues. Each experiment is a candle against the dark, a bid to identify the unseen majority of existence. But whether or not we ever detect them directly, relic particles will shape the universe's last epochs. In the silence after black holes have evaporated, neutrinos and photons will remain as the thinnest soup of radiation. If axions or other light fields exist, they may persist indefinitely, cold and weak, yet eternal. The ultimate universe may be a sea not of stars, but of faint particles, stretched across infinite distances, their energies so low they scarcely count as real. Philosophically, this prospect is both humbling and profound. It means that the cosmos does not end in nothing, but in almost nothing, a thin residue of particles too quiet to form, too weak to change, yet stubbornly present. Existence does not vanish entirely, it dwindles, fading asymptotically toward emptiness but never quite arriving. The relic particles are the final guardians of memory, though they remember nothing. They are the last actors on the stage, though their performance is silent. To imagine them adrift in an endless dark is to glimpse the ultimate austerity of physics, a universe reduced to whispers that no ear will ever hear. And so, neutrinos, axions and their kin remind us that the end is not absolute. It is a fading, a thinning, a persistence of almost nothing. The curtain falls, but a faint vibration remains, like the echo of a voice long after the singer has gone. If relic particles will be the quiet residue of the cosmos, then black holes remain its last great storytellers. They are not merely remnants of stars, but monuments of gravity, keepers of memory, and performers in the universe's longest drama. In the far future, when galaxies no longer shimmer and stars have gone dark, black holes will still reign. The universe will be filled with them, stellar, mass black holes, born from collapsed stars, intermediate, mass black holes, their origins uncertain, and above all, the supermassive giants anchoring galaxies, weighing millions or billions of solar masses. These titans will dominate the darkness, their horizons marking the last thresholds of significance in an otherwise barren sky. For a time, they will grow. As stars exhaust themselves, black holes will feed on their corpses. As galaxies drift apart, local clusters will merge, and black holes at their centers will coalesce into still larger beasts. The last galaxies will become graveyards ruled by singularities, dancing through long spirals until they collide. Each merger will release torrents of gravitational waves, trembling ripples that spread forever across the expanding void. And then begins their long unwinding. According to Hawking, black holes are not immortal. They radiate, slowly bleeding energy into space. For stellar mass black holes, evaporation requires 10 to the power of 67 years. For supermassive ones, the timescale stretches to 10 to the power of 100 years or more. These numbers dwarf any scale we can comprehend. For aeons beyond aeons, black holes will sit as the last structures, waiting in silence, shrinking imperceptibly. When evaporation nears its end, the quiet giants will flare. As they lose their final mass, their temperature rises, their radiation intensifies, until they burst in a brief blaze of high-energy particles. Each death will be a lonely firework, lighting the dark for an instant before fading forever. There is deep poetry in this vision. Black holes are both destroyers and preservers. They swallow light, matter, and information, hoarding the stories of the universe within their horizons. Yet in the end, they return it not as coherent memory, but as radiation, scattered into the void. They are libraries that burn slowly, releasing their pages not in words but in photons and particles spread across eternity. In their long reign, black holes define the universe's final soundtrack. Each merger, each evaporation, each ripple of gravity is another verse in the last epic poem. They do not speak loudly, but they endure longer than anything else. In a cosmos where even protons may decay, black holes outlast all familiar matter. They are the guardians of the final night. Philosophically, they are metaphors of impermanence. Even the densest, most unyielding structures must one day dissolve. Even horizons, which seem like eternal boundaries, are temporary veils. The very idea of permanence collapses with them, showing us that nothing, not stars, not galaxies, not even space-time's deepest wells can resist the entropy of eternity. When the last black hole sighs its final radiation into the void, the universe will be stripped of structure. Only diffuse particles will remain, whispering into silence. But for trillions upon trillions of years, black holes will have been the last storytellers, patient, dark, and inevitable. When the last black holes evaporate, the cosmos will no longer contain structures. Yet even in this emptied stage, the mathematics of space-time continues to whisper. The future of a universe dominated by dark energy is described by the geometry of de Sitter space, a solution to Einstein's equations where expansion never ceases, where horizons define the limits of what can be known. In this geometry, even emptiness has properties, and even silence has a temperature. Physicists Stephen Hawking and Gary Gibbons showed that de Sitter space, much like a black hole, possesses an entropy and a temperature. The Gibbons-Hawking temperature is astonishingly small, but not zero, a faint thermal bath arising from quantum fields in curved spacetime. Entropy, the measure of disorder, is tied to the area of the cosmological horizon, the ultimate limit of what any observer can see. In this way, the end of the universe is not an absolute void, but a system with thermodynamic properties, as though even nothingness must obey the laws of heat. The entropy of de Sitter space is vast, far greater than the entropy of all the black holes and stars combined. It suggests that the final state of the universe is not merely disordered, but maximally so, a state where all possible configurations of matter and energy are equally likely, and none has preference. In this final dusk, the universe is not destroyed. It is dissolved into a sea of uniform possibility. Yet this uniformity raises deep puzzles. If horizons carry entropy, what information do they conceal? In black hole physics, the question of information loss remains one of the greatest mysteries. In cosmology, the same riddle applies on a universal scale. If galaxies disappear beyond horizons, is their information lost forever? Or is it somehow encoded on the horizon itself, preserved in a way we do not yet understand? These questions tug at the very foundations of physics, linking the fate of the universe with the quantum nature of space-time. Mathematically, the end is cold. The temperature of de Sitter space is unimaginably small, just above absolute zero, a thermal whisper that stretches infinitely. The photons that remain will be so faint, their wavelength so vast, that they are indistinguishable from emptiness. And yet, the equations insist they are there. The last light is not the blaze of a dying star, but the pallor of horizons glowing faintly with quantum uncertainty. Philosophically, this final state is haunting. It tells us that even nothingness has texture, that the end of all things is not silence but a thin hum of existence spread across eternity. It suggests that the universe cannot fully vanish, for even void carries entropy, even emptiness carries memory. To imagine this is to stand at the threshold of mathematics and metaphysics. The end of the universe is not fire, not collapse, not tearing, but a settling into equilibrium, so perfect that it becomes indistinguishable from nothing. Yet beneath that stillness lies a structure entropy, as vast as the cosmos, horizons glowing faintly, space-time itself holding its last, soft breath. As the mathematics of horizons and entropy sketch the cold geometry of the end, a deeper question stirs. What does such an ending mean? Beyond physics and numbers, the universe's silence presses against human thought, inviting reflection on value, permanence, and the fragile spark of consciousness in a cosmos destined for dissolution. The picture is stark. Stars vanish, galaxies drift beyond horizons, matter itself may decay, and the last black holes evaporate into whispers of radiation. What remains is uniformity, maximum entropy, a sky without stories. In this state, there is no memory, no change, no distinction. The arrow of time loses its direction. For physics, this is equilibrium. For philosophy, it is erasure. Yet within this vision lies a paradox. If the universe will one day become featureless, does that make its present richness meaningless? Or does it make it all the more precious, precisely because it is fleeting? The knowledge of impermanence sharpens awareness, turning every star, every breath, into something irreplaceable. The cosmos itself teaches us that transience is not failure but reality. For some, the idea of an ending evokes despair, a sense that nothing we do can matter if it is destined to vanish. But for others, it brings freedom. If permanence is impossible, then meaning does not lie in endurance but in presence, in the fact that, for a brief moment, the The universe knows itself through us. The stars burn, the galaxies spin, and we, born of stardust, reflect upon their fate. That reflection is itself a kind of resistance to oblivion. Science, in its precision, often speaks in numbers and probabilities. But at the edge of cosmology, when the subject is the end of all things, science becomes poetry by necessity. It cannot help but ask the same questions that haunt philosophy and art. What is beauty in a vanishing universe? What is value when nothing lasts? What does it mean to exist, knowing existence is temporary? Perhaps the answer lies not in permanence, but in participation. We are not separate from the cosmos, we are its fleeting expression. Our thoughts, our loves, our questions are as much a part of the universe as galaxies and black holes. In contemplating the end, we are the cosmos contemplating itself, aware of its own impermanence. That awareness, though temporary, is profound. The thinning sky becomes a metaphor not only for cosmic fate but for human life. Just as stars burn brightly before fading, so too do lives blaze with moments of brilliance before returning to silence. The end of the universe mirrors the end of the individual, and in both cases, the absence of eternity does not erase the value of the moment. In the final analysis, cosmology and philosophy converge. The universe will not last forever, but in its brief arc from fire to silence, it has given rise to complexity, to life, to thought. To know this, and to reflect upon it, is to find meaning not in endlessness, but in the fragile, transient glow of being. The fate of the universe may be vast, but its contemplation always comes home to the scale of human life. What does it mean for us, ephemeral beings, to dwell in a cosmos destined for silence? The night sky, filled with galaxies, seems eternal to our eyes, yet we now know it is not. To imagine its vanishing is to imagine our own impermanence writ large. Cultures across millennia have wrestled with endings. Ancient myths spoke of cosmic floods, of fiery purges, of endless cycles of destruction and renewal. The scientific visions we now hold, heat death, Big Rip, vacuum decay, are no less mythic, though grounded in data rather than legend. They are our era's stories of finality, told not with gods and monsters, but with equations and telescopes, and yet their emotional weight is the same: awe, fear, wonder, and reflection. For artists, the end of the universe has inspired canvases, poems, symphonies. Painters have sought to capture the fading of light, composers the swelling of silence, poets the melancholy of impermanence. Science, far from replacing these visions, enriches them, offering detail, texture, imagery of galaxies dissolving and horizons glowing faintly. Knowledge becomes metaphor, mathematics becomes myth. For philosophers, the cosmos's fate presses questions of meaning. If all things vanish, what is the worth of beauty, of love, of thought? Some argue that meaning must be eternal to be real. Others suggest that transience itself grants significance. Just as a flower is precious because it blooms only briefly, so too is life valuable because it glimmers against the darkness of cosmic time. For science itself, the question of endings is not only theoretical but deeply human. To measure supernovae, to map galaxies, to detect gravitational waves, these are acts of curiosity, but also acts of courage. They are humanity's way of asking the largest possible question: what is the destiny of everything? And in the asking, we affirm our place as participants in the universe, not separate from it. We may not live to see the sky go dark, but we live in the knowledge of it. That knowledge shapes culture, art, and thought. It humbles us, but it also empowers us. To know the stars will vanish is to cherish them while they shine. To know galaxies will recede is to treasure the brief window in which we can see them. To know that the cosmos itself may one day be gone is to find meaning not in eternity, but in presence. The human scale is small, but it is not insignificant. For in contemplating the end of the universe, we engage in an act of cosmic self-awareness. We are the universe reflecting on itself, pondering its own impermanence. And that act, brief, fragile, finite, is perhaps the greatest meaning the cosmos will ever hold. And so, the long story of endings draws to its final scene. The physics has spoken in many voices, the steady whisper of entropy, the thunderclap of acceleration, the eerie silence of metastability. Each possibility, heat, death, rip, crunch, decay, or cycle, offers a vision of how the universe may close its eyes. Yet beyond the data and the theories, beyond the telescopes and the equations, there is the simple, unyielding truth: everything that begins must end. In contemplating that end, we glimpse a mirror. The universe is vast, stretching across billions of light years and billions of years, but its fate echoes our own. Stars are born, they blaze, they fade. So too do lives. Galaxies drift apart, memories dissolve, structures unweave. The cosmos teaches us what we already know in our hearts, that impermanence is the rule, not the exception. And yet, within impermanence lies beauty. To imagine the universe fading is not to despair, but to see more clearly the miracle of its present. For we live in a privileged moment, a cosmos bright with stars, a sky filled with galaxies, a universe young enough to be full of stories and old enough to have revealed its beginnings. We are here, between origin and end, alive in the rare interval when the cosmos sings. Perhaps this is what matters most. The universe does not owe us permanence, but in its brief blaze, it has given rise to beings capable of reflection, of awe, of love. In knowing the end, we learn to cherish the now. Every star in the night sky is a reminder, not of eternity, but of fragility, and of the strange beauty that fragility creates. In the far future, when galaxies are gone and silence reigns, no witness may remain. But here, now, there is witness. Here, now, the universe knows itself through us. That too is part of its story, perhaps the most delicate and profound chapter of all. And so the narration slows, the language softens, the imagery fades like the last light of a dying star. The end of the universe is not a scream, not a sudden crash, but a long hush, a drifting into silence. It is not destruction but release, not violence but rest. Imagine it, a final horizon, smooth and unbroken, stretching endlessly. No galaxies, no stars, no matter. Only the quiet hum of space-time, the faintest echo of what once was. The curtain falls gently, without resistance. The universe exhales, and in that stillness there is peace. The journey of endings is complete, and yet the story does not close in darkness, but in calm. For though the universe may fade, though stars may die and horizons swallow memory, the silence that awaits is not cruel. It is soft, like a lullaby, like the final notes of a symphony that does not stop but lingers. We, who live in the middle of this vast narrative, are not powerless before it. By knowing, by wondering, by imagining the future of all things, we give shape to meaning. The stars above us are already ancient, their light a letter written long before we were born, and yet we read it, we marvel, we weave their glow into our stories. That act, however brief, defies the emptiness. Perhaps this is the truest gift of cosmology, not to predict the future with certainty, but to teach us how to dwell in the present with reverence. The knowledge that the cosmos will one day fall silent makes the sky more luminous now. The awareness that galaxies will vanish makes each glimpse of them more precious. The recognition that all things end makes every moment of being more alive. So let the thought of the end be not a shadow, but a quiet light. Let it remind us that the universe is fragile, and that its fragility is its beauty. Let it teach us that meaning is not in eternity, but in the fleeting, in the brief, in the fact that we are here at all. The cosmos will one day close its eyes, but until then, it dreams through galaxies, through stars, through life, through us. And in its dream, there is wonder. Sweet dreams.